Hello everyone. Welcome to Linkfitty's Deep Dive. If you liked our previous podcasts or like this one, remember to subscribe. Okay, so we've got this Qwen2.5 Omni, the thing you sent me, or this report.
It's a pretty done stuff. It looks like they're going for like a single model that can work with like everything: text, images, audio, you name it, even video, and it can generate text and speech like on the fly, streaming like real time, you know.
Yeah, that real-time part is it's a big deal for people like our listeners, data scientists, AI developers. The real story here is this the integration. It's not just like a bunch of different models stuck together. They built this thing from the ground up to handle all these different types of data and then to actually do something with it. Generate stuff. Right? And for our listeners, folks who want to get up to speed fast, this deep dive's like the shortcut. We're going to unpack how this Qwen2.5 Omni, how it chews through all this data, how this thinker-talker setup works, how they pull off the real-time stuff, the training, and of course the benchmarks. Got to see how it actually performs.
So, first things first, how does this thing even make sense of like text, images, sounds, video all at once?
Well, they use this block-wise processing thing for the audio and video. Basically, they break down these long streams of audio and video to like bite-sized chunks. Makes it way easier to handle. Like imagine trying to read a whole book at once versus taking it chapter by chapter.
Okay, so that's how the raw audio and video gets like initially processed. Then the main language model, that's where it comes in to put all these pieces together, right? Sort of like we have our senses they take in the world and our brain makes sense of it all.
Yeah, exactly. And because of the split, they can use the shared attention thing that transformers are so good at. It's like they can merge all this sensory info much more effectively. But the real challenge, especially with video that has audio, is keeping everything in sync. That's where this Time-alignedMultimodal RoPE comes in. TMRoPE, they call it.
TMRoPE. Yeah, sounds like they're the key to making this whole multimodal thing tick. The report says it like aligns those audio and video timestamps.
How does it do that?
Well, think of TMRoPE as a way to give every piece of data a unique address in time and space. It's got three parts, one for time, one for height, and one for width. And it works for all the different types of input they're using. They took the old multimodal rotary position embeddings and added this really precise temporal information. So basically, it can tell you where something is in time and where it is in the image or video frame. Super clever.
Okay, I'm following. So for text, like words in a sentence, how does TMRoPE work there?
For text, it's pretty straightforward. All three components, time, height, width, they all use the same position ID. So it's basically just keeping track of the order of the words like a normal position encoder would.
Okay, that makes sense. But audio has like duration, but not really height and width.
Right, so for audio, the height and width, those are like ignored. But the time part, that's where it gets interesting. Each temporal ID, it represents a 40 millisecond chunk of audio. It's like marking time as the audio plays.
Got it. What about images? They have those spatial dimensions, height and width, but they're not like changing over time in the same way video does, right?
So for images, the time ID stays the same for every part of the image, but the height and width, they get unique IDs based on where they are in the image grid. So the model knows like this object is in the top left, this one's in the bottom right, and so on.
Okay, I see. And then video, especially with audio, this is where the whole sensing thing really matters, right?
Absolutely. The audio part that's still encoded with those 40 millisecond time IDs, just like regular audio, but for video each frame gets its own increasing time ID, so it knows how the video unfolds over time. And the height and width IDs for each frame, they work just like images, capturing the spatial info.
Now, the report also mentioned like dynamically adjusting these time IDs based on the actual time between frames. Why do they do that?
Oh, right. Because video frame rates, they can be all over the place. So, to make sure that each time ID always represents 40 milliseconds, they got to adjust the increment based on the real-world time difference between those frames. That way you get perfect audio-visual sync, no matter the original frame rate. Pretty neat, huh?
Yeah, that's clever. Now, when you have like text and video with audio all together, how does it keep track of everything?
Simple. They just keep position numbering going. So, like if the text ends at position 100, the audio might start at 101. This way you've got one continuous stream of IDs across all those inputs, and the attention mechanisms can work their magic across everything.
So TMRoPE, it's like this universal coordinate system for all the data. The report also talks about a time interval algorithm. What's that for?
Ah, yeah, that's shown in figure 3. It's all about making the model process video and audio together smoothly. They chop the video with its audio into these little 2-second bits. Then within each bit, the video part comes first, then the audio. It's like show a silent clip, then play the sound.
So, they're creating these like mini audio-visual packages. Makes sense.
Exactly. That way, the model can easily learn the connection between what it sees and what it hears within in that short window.
Okay, let's get specific. How do they prepare each type of data? Text is probably the most straightforward, right?
For text, they use their Qwen tokenizer, the usual setup byte level BP of a vocabulary like union 51,000 tokens. Pretty standard stuff.
And for audio?
They resample the audio to 16 chess, then turn it into a MEL spectrogram, 128 channels, 25M window, 10M the whole deal. It's basically turning the sound in visual representation of its frequencies over time.
And that goes into the audio encoder from what was it? Qwen2 audio.
That's the one. And they designed it so each output frame matches up with roughly 40 milliseconds of audio, keeps everything nice and consistent time-wise.
Okay. So, for images and video, they both go through that vision encoder from Qwen2.5 VL, right? That's the one with like 675 million parameters.
That's right. It's based on the vision transformer architecture, and they actually train it on both images and video. So it's good at understanding both still and movie of visuals dynamic frame rate for video. That makes sense. And they do this weird thing where they treat each image as 2 identical frames.
Yeah, any idea why?
My guess is it's a way to give those still images a tiny bit of temporal context. It probably helps keep the processing pipeline consistent for both images and video. And it lines up nicely with that 40 millisecond thing they do for audio.
Clever.
Yeah, so we've covered how the data gets in. Now, the main attraction, this Binker-Talker architecture, that's where the magic happens, right? Generating text and speech at the same time.
Yeah. And it's actually pretty elegant. If you look at figure 2 in the report, the thinker, that's basically your standard transformer decoder, like the heart of a language model. It takes in all that multimodal input, and it spits out both high-level representations and the actual text output.
Okay, so the thinker is the one doing the deep thinking, coming up with the words. What about the talker?
The talker, that's another transformer decoder, but it's specifically for generating those speech tokens. And the cool thing is it doesn't just work in isolation. It gets those high-level representations from the thinker. So, it knows the meaning and the intent behind the words, and it also sees the entire history of what the thinker has processed. So, it's got all that context like different parts of our brain working together, right? Coordinated.
Exactly. The whole system is trained end to end, so they learn and work together as one.
But why does the talker need both those high-level representations and the text tokens from the thinker? Seems like one or the other would be enough.
Ah, good question. The high-level stuff that's for the tone and attitude of the speech. Yeah, you know how the same words can sound happy or sad, angry or excited. That all comes from those representations.
Okay, so that's for the emotion. But why the raw text tokens too?
Because those high-level representations, they're great for meaning, but they might not always distinguish between words that sound alike. You know, like there and there. By giving the talker the actual text tokens, it knows exactly which word was intended and can pronounce it correctly.
So, it's like meaning plus wording, and that gives the talker everything it needs. They also mentioned this WZE tokenizer thing. What's that about?
Oh, that's their speech codec. It's like a super efficient way to represent the important info in speech. This is crucial for streaming because you want to keep the data size down, and then they can decode these tokens back into a smooth audio waveform using a causal audio decoder. And I noticed they don't require a strict word-by-word timestamp alignment for the speech. That seems like a big simplification.
It is. It means they don't need those super precise labeled data sets, and it makes the real time generation way easier. The talker can just focus on the overall flow and how the speech should sound without getting bogged down in the tiny details of timing.
All right, thinker-talker, check. Now let's talk about the real-time aspect, the streaming. The report makes a big deal about minimizing the initial delay. Why is that so important?
Well, think about any live interaction, especially with video calls or like voice assistants. If there's a big pause before you get any response, it just feels awkward and unnatural.
Makes sense. And that delay comes from a bunch of things, right? Processing the input, generating the first speech token, converting that to audio, and just the inherent latency of the whole architecture.
Yep, all those things. So, to minimize the time spent processing the input, they've tweaked the audio and visual encoders for block-wise streaming. This is key for prefilling, which basically means starting to process the input as soon as it comes in instead of waiting for the whole thing.
So how does that block-wise processing work for the audio and visual parts?
For the audio encoder, it now focuses its attention on those 2-second blocks we talked about. Way faster than trying to handle the whole audio stream at once. And for the vision encoder, they use flash attention, which is super efficient. And they also merge neighboring tokens with a simple MLP layer.
So, by breaking the input into chunks, they can start generating output much sooner. Now, there's also this sliding window block attention thing for the streaming codec. That sounds pretty complex.
Yeah, it's how they generate the audio waveform in real time. They use this flow matching DIT model, which is like a fancy neural network. And to make it stream, they group the speech codes into blocks and then restrict the attention so each block can only see a few neighboring blocks.
Like in Figure 4, they show how the attention mask limits the receptive field to 4 blocks. Yeah.
2 before the current one and 1 after.
Exactly. So as the model is decoding, it generates the MEL spectrogram chunk by chunk. That way each chunk has the context it needs to sound good and coherent. And then they use big VJN, which is a vocoder, to generate the final waveform, also chunk by chunk.
So it goes talker makes speech tokens. Then the DIT thing turns those into a MEL spectrogram and big VJN makes that into sound. And this whole block by block limited attention. That's the key to keeping the delay below.
You got it. It's all carefully designed to make the experience as smooth and real time as possible.
Okay. So much for the architecture and the streaming. Now, how do they actually train this beast? The report mentions a 3-stage pre-training process.
Yeah, the pre-training is all about giving the model a solid foundation. In the first stage, they actually freeze the main language model, the LLM, and just focus on training the vision and audio encoders. They use tons of audio text and image text pairs. Basically, they're teaching those encoders to understand and sounds in a way that the LLM can already grasp.
So the encoders are learning the language of the LLM, even though the LLM itself isn't changing yet. What happens in the second stage?
Then they unfreeze everything, the whole model, and start training on a much wider range of data. We're talking 800 billion tokens of image and video data, 300 billion audio tokens, and 100 billion tokens of video with audio. That's when the real magic happens. The model starts to connect all the dots, learning how these different modalities relate to each other.
It's a huge amount of data. And the third stage is all about long sequences, right?
Yeah, in that final stage they train with sequences up to 32, 70, 68 tokens long that helps the model deal with really complex lengthy inputs like long conversations or extended audio and video. They also use a really diverse mix of data for pre-training. Image, text, video, audio, text, and just plain text.
Right? They're really throwing everything at it. And they follow the lead of Qwen2 audio and replace those old-school hierarchical tags with natural language prompts that helps the model become more flexible and better at understanding instructions.
So when they started pre-training, what were the initial settings for each part of the model?
The LLM that was initialized with the weights from Qwen2.5, the vision encoder came straight from Qwen2.5 VL, and the audio encoder started with the weights from Whisper Large V3. So they're building on a lot of existing knowledge. And they did this clever thing, where they trained the encoders and their adapters separately at first, while the LM was still frozen.
A pretty sophisticated approach.
Yeah, it is that second stage where they train everything together. That's really crucial for getting the model to understand how different modalities interact. And by keeping the text data in the mix, they make sure the model doesn't forget its core language skills. They even mention how they started with a limit of 8,192 tokens and then pushed it to 32,768. They really wanted to handle those long contexts.
So pre-training is done. Then comes post-training, right? Yeah, where they fine-tune the model for specific tasks and really polish the SDE generation, right?
For the thinker, the text part, they use a bunch of instruction following data in the chat format. They've got pure text conversations, visual conversations, audio conversations, and mixed modality stuff, too.
And the talker that gets its own 3-stage post-training process.
Yep. First, they do context continuation learning, which basically means teaching it to generate speech that flows naturally from what came before. Then, they use direct preference optimization or DPO to improve the quality and stability of the speech. They actually use reward scores based on word error rate and punctuation pause error rate to guide this optimization.
So they're making sure the speech is not only accurate, but also sounds natural with the right pauses and intonation. What about that third stage for the talker?
That's multi-speaker instruction fine-tuning. They're basically exposing it to a bunch of different speakers and speaking styles within the context of instructions. This helps the talk become more versatile and learn to adapt its voice and style to fit the situation. And they also use in-context learning ICL for the talker. That's where it learns to predict the next speech tokens in a conversation. Right.
Right, but unlike the thinker, the talker also gets to see the spoken responses. This helps it learn how to map meaning to speech, how to capture things like prosody and accent, and they also do some fancy stuff with timbre disentanglement to make sure the model doesn't start associating specific voices with specific words.
So they fine-tune it to specific speakers as well.
Exactly, that way the talker can really personalize the speech, making it sound even more natural and engaging.
So, they put a lot of work into both understanding the input and generating high-quality speech. But how does it actually perform? The report has a pretty extensive evaluation section.
It does, and they split the evaluation into 2 parts. Understanding, which is basically input to text, and speech generation, which is input to speech.
Okay, so let's start with understanding. They tested it with text, audio, image, and video inputs.
For text, they used a whole bunch of standard benchmarks, things like MLU Pro, LibNGOEA3, GPA, GPQA, GSM, all the usual suspects. And as you can see in Table 1, 2.5 Omni pretty really well. It's generally between Qwen2.5 and Qwen2.5 and it beats the smaller Qwen2.7 on most of them.
What about audio detect?
For that, they focused on benchmarks like MMAU and Voice Bench, looking at things like speech recognition, translation, emotion recognition, and even music understanding. Tables 2, 3 show that it's either state-of-the-art or very close to it on all those tasks. It's really good at audio reasoning, especially on MAU, and it's also great at voice interaction according to Voice Bench. They even have their own voice chat benchmark, and Table 4 shows that Qwen2.5 Omni is significantly closer to the text-instructed models than its predecessor, Qwen2 Audio.
Impressive. Now, what about image to text?
They compared it to 0.5 EL7B and other open-source Omni models. Table 5 shows the results. It's on par with Qwen2.5 EL7B, and it actually beats those other open-source models on a lot of the benchmarks like MMU and Math Vision. It even outperforms GT4 Mini on some tasks, and Table 6 highlights its really strong visual grounding capabilities.
And for video to text without any audio?
For that, they use benchmarks like Video ME and MV Bench. Table 7 shows it beats other open-source Omni models in GPT-4 Mini, and it's competitive with 2.5 EL7B, even though that one's specifically designed for vision tasks.
So for the ultimate test, multimodality detect, where you can have any combination of inputs.
They use the OMNI benchmark for that, and the results are in Table 8. Qwen2.5 Omni absolutely crushed it. It's way ahead of any other OMNI model out there.
So the understanding part, that's a slam dunk. Now let's talk about speech generation. They looked at both zero-shot and single speaker settings, right?
For zero shot, which means generating speech in voices it hasn't been trained on, they use the seed benchmark. Table 9 shows that it's pretty competitive in terms of both accuracy and speaker similarity, and it gets even better after they apply reinforcement learning optimization.
And for single speaker where it's fine-tuned to a specific voice.
They use their own dataset for that, and Table 10 shows the results. After fine-tuning, it gets near human quality in terms of naturalness, and it still maintains high accuracy.
So it can understand. It can generate speech, and it does it all in real time with low latency. Pretty amazing stuff.
Yeah, the results really back up what they claim in the report. Yeah, Qwen2.5 Omni is a major step forward, and it opens up a lot of possibilities for new applications.
So for our listeners out there, the data scientists and AI developers, what are the key takeaways here?
I'd say the biggest thing is this. We're now seeing truly unified multimodal AI models. Qwen2.5 Omni can handle text, images, audio, and video altogether. It can generate text and speech on the fly, and it performs incredibly well across a wide range of tasks, and the technical innovations they came up with to achieve that. They're pretty groundbreaking too. TMRoPE, the thinker-talker architecture, that blockwise streaming approach. These are big deals.
Absolutely. And the results they're getting on those benchmarks, especially OMNI bench, that's state-of-the-art stuff. Plus, the ability to do speech instruction following. That's really pushing the boundaries of what these models can do.
But like they mentioned in the report, there's still room for improvement. Things like video OCR and getting a deeper understanding of how audio and video work together, those are still open challenges.
Yeah, they acknowledge that, and they call for more collaboration between researchers and developers to create better benchmarks and data sets. That's going to be key for future progress.
They also see this work as a step towards AGI, artificial general intelligence. A bold claim, but maybe not so far-fetched anymore, right? And their future plans are pretty ambitious too. They want to build even more robust and efficient models, ones that can generate not just text and speech, but also images, videos, even music.
Wow, that's pretty exciting. Future. So for our listeners, I'll leave you with this. These unified multimodal models, they're changing the game. They're getting closer and closer to how we humans communicate and understand the world. So what does that mean for the applications you're building? What new possibilities does it open up? What challenges does it create? It's something worth thinking about. Thanks for joining us for this Linkvideo's deep dive. Please like and subscribe if you want YouTube to continue notifying you about our podcasts.